warm-up for the day. So go ahead and read through. On this slide, we've got some review from what we talked about in lecture on Wednesday. On the right-hand side, we have 3 situations. If you remember, Wednesday's lecture was all about this idea that there's something called an ADT. That is the theoretical expected implementation or expected behavior of something, different from the data structure, which is like the actual code that you would write in order to accomplish that thing. And in this course, the open question is always going to be, what type of design, what type of functionality do we need to do in order to make this scenario? And then what type of data structure are we going to use to accomplish that to optimize for our specific situation? So we've got 3 situations on the right-hand side. I want you to take a couple minutes, talk to the people around you. The best part of this is I have not given you enough information on the right-hand side for there to be only one answer to this question. Yeah, I know. You are like, oh, computer science is so great because there's always a right answer. Life is ones and zeros, black and white. No more. Welcome to the gray area. Okay, so take some moments. Remember what we talked about on Wednesday. There is a poll everywhere live where you can record your answers. We are going to come back and debate this at the end of lecture today. But poll up, poll everywhere. Make sure you can log into it and take a few minutes and discuss these scenarios with those around you. We'll come back together at, let's say, 2 minutes from now. Go. Maybe like introduce yourself. Be that cool person that sees someone not talking to anybody and like be their buddy. TAs also, if you want, feel free to wander around, answer some questions. If you just joined us, we're debating the scenarios on the screen. Please feel free. Love it. Yes. Good clock in this room. Take like 1 more minute to wrap up these conversations. Maybe you know which one you would pick, but you better be able to justify why it's that one and not the other one too. It's not enough to just say why one is good. You got to say why it's better than the other one. Yeah? Yes. I love this. All right, in the interest of time, we're going to slowly wrap up our wonderful debates. Reminder that there is a poll everywhere question live, so maybe now's a good time to go lock in your answers. We're going to dive deeper into content, but before we do that, does anyone have any questions or initial thoughts that we want to talk about here about our warm-up? Any questions that came up? Any unresolved debates amongst group members you would love to share with the class? Let's see. Yeah, anything? No? Ooh, okay. All right. So, and here's the thing, right? In each of these scenarios, I gave you like one sentence. That is not at all enough information, right? I'm going to take a moment here. Each of these situations could easily be an example of an interview question. And you might be like, Casey, we're going to code for 45 minutes. There's a sentence and a half on each of these things. And that sometimes, my friends, is exactly what that interviewer is trying to do to you, because they want to see, are you going to ask questions or are you going to make assumptions? And when you make assumptions, do they come from your own empathy? Do they come from your awareness of the customer? How do you figure these things out? So when you guys picked linked lists, can I ask maybe what aspects of a playlist did you talk about that you think this would optimize for? Did you kind of have conversations about how you'd use the playlist at all? Yeah. Mm-hmm.
You're not always going to be removing like the first or last song. And so with a linked list, it's a lot easier to insert things and remove things in the middle of the list. Whereas with an array list, that's very more complicated.
Perfect. Thank you. Thank you for sharing a perfect example, right? So in this scenario, I didn't say anything about how big these playlists were or how often you change them or any of the features, but it sounds like based on your group, and hopefully we have some type of personal lived experience or cultural touch points to a playlist like this. And in your scenario, we're talking about, you know what? We like to insert stuffs in the middle. Let's be real. You have to curate the progression of that playlist, right? You know people going to judge, all right? Are you an all rise playlist? Are you a rise and fall playlist? Are these things going to grow and shrink? And a linked list, I absolutely agree, would be the type of data structure that would optimize for the flexibility to change position and change the overall size. Anybody else here? Maybe talk about a different aspect of playlists. Or do you have a question? Yeah, please.
Oh, yeah. I was going to say we thought an array list.
Okay, sure. Why?
Good option. So we thought in the sense like when you're looking for a song,
Mm-hmm.
if you click on a certain song, you just kind of want the index of it.
Mm.
So if you just get its index, and you get the song.
So, and again, welcome to the gray area. I absolutely agree just as much. So in this scenario, we're instead talking about, well, maybe instead we're not thinking about optimizing for moving around within the playlist. We're thinking about, hey, when I'm looking at a playlist, I want to be able to jump right into the middle of that like third song. Anybody else talk about any other sort of functionalities of the playlist that might help us pick which one we're going to optimize for? Yeah.
We discussed about shuffling the playlist, and because of that, we chose array list because it's easier to shuffle than linked list.
Another, thank you, perfect example. So if we were going to say perform a shuffle, and I will be real, I'm one of those people that like my Spotify is on default shuffle all the time because I choose just chaos, I guess. And so in that situation, we need to generate random numbers to figure out that order of the playlist. And it would be a lot easier in order to figure out how to construct that new random order if we have easy access based on the indices, right? Congratulations. All of you have correctly selected a proper data structure implementation. And all three of those things that we just talked about are exactly what I would want to hear in an interview and frankly, in any type of software engineering design room as to why you thought through and picked those things. Because the reality is we could do a lot of things a lot of different ways, but usually there's sort of like one or two scenarios that you really want to optimize for. Now, we just talked about how to optimize for it. I'm going to talk throughout this lecture in a few other ways to think about what it really means to say optimize and how we get to some kind of specific academic language around it. But while we're going through, another way to also start to think about things like I mentioned sort of at the end there is you can also start to think about, well, which one of these things are the opposite of optimal. Which one of these things are the most inefficient for your optimal situation? Sometimes you're like, ooh, yeah, I need those indices because I need to shuffle it. Or sometimes you're like, well, maybe shuffle is important, but I just know having to loop through and find all of the indices is going to be so suboptimal that I have to also avoid the linked list. So you got to think about it from all those different angles. Like I said, I've got a slide with these on again. We'll talk about it a little bit more as we get deeper into lecture. But just want to kind of clean up our administrivia for a second. So thank you all for your patience. We should have the slides posted to the course website now. So if you go onto the main page of the course website, cs.washington.edu/373, and you scroll down through the calendar section, you'll see that there's links to the slide decks. We're going to continually add those. We're going to preload some of the slides. I will tell you, like, let's be real, I was fidgeting with these slides until like 10 minutes before I left my office. So these things may change, but then at least you'll be able to sort of look ahead, especially if you're somebody that likes to take notes. Also, of course, reminder that we have our first programming project out. I know it's working because congratulations to people that are already making those submissions in Gradescope. Remember that as you submit things, you get your points back. It's a great way to see how you're doing. The project will be due next Wednesday, the 6th at 11:59 p.m. Also, we are officially going to start office hours with the TAs starting on Monday next week. On the course webpage, you can go to the office hours page and you'll see our Google Calendar for the office hours. Make sure that when you're looking at that calendar, you check where the location of the office hours are. Also, right now, all of our office hours are in person. There's one hybrid option. We're going to add a couple digital only options just for those of you that need to make sure that you're minimizing your exposure. We do have some, we'll call them pre-office hours yesterday and today. I just realized it's Friday. Thanks to our wonderful TAs that are there to help you figure out if you have any setup problems. So you can go look at that. If you need somebody to come take a look, your JDK isn't loading, your IntelliJ is doing weird stuff. So we have some help on that. Also, keep in mind, you are more than welcome to use the Ed board to ask questions about your programming assignments or ask questions about setup. If you want to post like your code, like maybe you're having some exception you can't figure out or something's not behaving right, you are more than welcome to post your code for us as staff to review, but just make sure that you make that post private. Does anyone have any administrative questions about the course at this moment in time? Yes?
Are you going to be having office hours?
Yes, thank you. I will be having office hours. So I usually wait and let the TAs get first pick, and then I fill in the things that I think will be hard. So looks like I'm probably going to have my office hours Tuesday evenings, and I might throw some more on the calendar for Wednesday, because let's be real, I know y'all going to wait till Wednesday to do your assignments. You shouldn't, though. I did. I regretted it. Somewhere upon a time, adults told me not to do that, and I was like, ha ha, adults, and now I'm that adult. Life is cyclical. So I will have office hours specifically to answer any course questions. I also do have my Calendly if you ever want to set up a one-on-one to talk about anything course related or anything career related. Any other administrative questions? Okay, let's learn some programming. So this week is all about this idea of design decisions. As you can imagine, we're sort of laying this foundation because pretty much after this week, from here on out, we're just going to start moving through skill sets. Next week and the week following is going to be, I'm just going to give you a heads up, real mathy, okay? And we're going to talk a little bit about that today. And if you're like, Casey, no, math scares me, I'll be like, hey, guess what? Me too. My AP stats teacher to my face was like, I don't know, girl, maybe you're just not made to be an engineer. I make so much more money than her now. That's like not a way to measure a good human or happiness or nothing, but does it make me feel a little bit better about how gosh darn passive aggressive she was with all of my stats homework? Yes, it does. So I too was honestly never a really big math person. You don't really need to be great at math to be great at programming, but you will find that programming is inherently a symbolic language to express logic, which is exactly what computer science is. So that's why a lot of times you'll find people that are good at math are also good at computer science, but they're not technically related. But I'm just giving you this heads up that we are going to do a lot of algebra in the next few weeks. Don't worry, we will provide as many resources as we can for you. And if you're like, Casey, what are we going to do all this math for? It's because we're going to start talking about some specific, sort of mathematical ways to assess and analyze the optimality of your code. So that's what we're going to do for the next few weeks. And then after that, data structures and algorithms, baby. We're just going to fill up your toolbox, okay? So, welcome to the math part. This is technically a review of something that hopefully would have been covered in 143, but I know that this is the thing that people usually forget first coming out of 143. So, you probably learned about something called Okay, I'm going to be real with y'all. This Surface has blue screened twice today already, so everybody send it the best vibes. Okay, so you may have heard of something called Big O. Big O is another way we use to sort of refer to this concept here. It's and we'll talk about where that comes in from. So here you can see Big O there. But really, this idea here is that when we think about how quickly the computer can execute the instructions we give it, that is something we call the runtime of our code. Now, we're going to talk in a lot of detail about what that actually means, but the runtime in this context refers to how many instructions are going to get executed in relation to how many pieces of data you are inserting into this algorithm. So for example, let's say I give you a linked list and I ask you to go in and find the last song in that playlist's linked list. Now they don't have indices, right? So I'm gonna have to start at front and then I'm gonna have to follow that little daisy chain of the references to get all the way to the back, which means if I'm trying to get that song at the very back of the list, I have to touch every single thing in the list. And by touch, I mean I probably have a loop that's going to loop from the front all the way to the back. So in this example, if I have 10 songs in the list, that loop is probably going to run 10 times. If I have 100 songs in the list, that loop is going to run 100 times. If I have 1,000 songs in the list, or 1,000 times. And so that relationship between how many times the loop runs and how many songs in the playlist is what we would call a linear relationship. It is directly related. As the number of songs in the playlist grows, the runtime will grow at the exact same rate. So if we were to graph the number of elements against the number of operations, if there were 0 songs in the list, it would take 0 time because it would iterate 0 times. If there were like 10 songs, then we would run 10 times through the loop. If there were like 100, we would run 100 times through the loop. So we end up with this type of linear structure. I just realized I drew it on this lovely logarithmic graph here, but you can see actually here is the linear line of what that might look like. So as the number of elements grows, the number of operations we execute grows in the exact same way. That relationship is called a linear growth rate, and its complexity, and that is its complexity class. The complexity class refers to that inherent type of relationship between how the runtime will change based on how you change the number of items put into the algorithm. We traditionally use the letter N to represent the number of items into the section. So you can see we have this N showing up everywhere. That's just us referring to how many things are in the data structure we're running the algorithm on. Other complexity classes. Let's say that we're using the array list implementation of the song playlist, and I want to always play the very last song. Do I have to loop over my array list to get to the very last song, or do I have an index that I can jump directly into? index. Agreed. So if I have 10 songs in the playlist, I would jump straight to index 9. If I have 100 songs in the playlist, I would jump straight to index 99. Is my code's runtime at all impacted by how many items are in my array list? No, it's not. This, then, is what we would call the constant complexity class. And what that means, and here's our little symbol for it, O of, and then we put the number 1 in there. And you might be like, why is it a 1? Just because literally it just means something that is not dependent on n. Some constant value. As it turns out, the constant is technically like mapped on here like somewhere like this, because the runtime does not grow at all in relation to how many items are in your data structure. And I will tell you now, this is it. This is the dream. This is the goal. If we can somehow write code that is just as efficient, runs just in the same amount of time for 1 million items in your data structure as for 10 items in your data structure, well, you've cracked it, y'all. That's it. How incredibly rare is it to be able to do this? In a lot of situations, it is impossible. But that is why constant is there at the top. So constant is a situation where there is no relationship, that the code always runs in the exact same amount of time, regardless of how many items are stored in your data structure. You can see some of the other complexity classes in here. We're going to talk about them in a lot more detail. You can see we sort of added a little bit of some example algorithms to help you. So for example, another one that I know, at least coming out of 143, was a little bit easier for me to sort of conceptualize is the quadratic. So for example, let's say if I had a collection of students in, let's call it some type of list, and I want to go through and check that there's no duplicate entries, what I could do is I could look at the very first student, and then I could look through every other single element and be like, hey, does this appear anywhere else in the list? And then I would come back and I'd look at the second student and I'd be like, okay, better go check everything else. Okay, does this appear anywhere else in the list? And then I'd move to the third one and be like, okay, does this appear anywhere in the list? In order to accomplish this, I probably would have an outer for loop that moves this hand, and then an inner for loop that compares all of those things against each other. So it would be a loop inside of a loop. So as you can imagine, if I had 3 students, that outer loop is going to run 3 times. That inner loop is going to run 3 times 3 times. That's the word times a lot. But you can imagine then, right, like for the first student, I look at the other 2. For the second student, I look at the other ones. For the third ones, I look at the other ones. If I have 10 students, the outer loop's going to run 10 times, and the inner loop is going to run 10 times for each of those 10. So we're going to end up with 100 total sort of executions. That nested loop then gives us what we would call quadratic relationships between the number of inputs and the actual runtime. And so you can see here that term big O, the reason we tend to abbreviate this to big O is because this is the symbolic way to express all of those concepts I just listed. We use the letter O, and then in parentheses, we put the complexity class sort of representation of how n grows in relation to the runtime, or how the runtime grows in relation to n. So in this situation, runtime doesn't grow based on n. There's no factor of n in this equation. In this linear situation, the runtime grows exactly in relation to how n grows, so we just put something in a factor of n. In that nested loop scenario, we run in what we would call n squared time, so it's the quadratic complexity class. Any questions about complexity classes or how this works at this moment in time? Yeah.
Is it also dependent on how many elements you have like inside of the for loop, for example? So like with that, would you just like scale it up in terms of like the big notation?
So when you say items inside of the for loop, do you mean like stuff that you're doing in the for loop that isn't just like looping over the array? Great question. Yes, that does impact the runtime. And in fact, we're going to get so deep into this that we're going to talk about every single bit of every character in the code and how it will impact runtime. And you'll find that actually we're going to get really, really specific and annoyingly pedantic about it. And then you'll find that actually a lot of the stuff doesn't really impact it. Like it just becomes so negligible in comparison to the other pieces that slowly we'll start to develop a gut understanding of, oh, okay, well, these things really impact runtime and I can kind of ignore this stuff. But until we get there, I'm going to get real specific and we're going to talk about it, I think Monday or Wednesday next week. Great questions. Cool. Yeah. Well, what an interesting question. The most inefficient complexity class. I think I currently have it slated for the second to last day of the class or the very last day of the class. We're going to talk about something called the P versus NP problem. Has anyone heard of that out of interest? Oh, okay, cool. If you have, this is me like annoyingly foreshadowing. Give it a Google. There is an unsolved problem in computer science because actually, as it turns out, there are so many algorithms that are so complicated, they would take so long to run, we physically do not have the type of computers that would even enable us to run them. For example, the traveling salesman problem, another thing to give a Google for funsies. We do not have a computer that can solve the traveling salesman problem. We're going to talk about how you distinguish between what can be resolved by our existing computers and what can't. Just because I'm an annoying nerd and I think it's really fun to Google this stuff, if you're like, Casey, I can't believe it. Don't we live in the future? Can't computers do anything? There must be some type of computer that can solve this. Quantum computing, y'all. Quantum computing. Doesn't technically exist yet. But Google it, all right? Okay, those are my foreshadowings for the last week of the quarter there. Okay, so like I said, we're going to talk about trade-offs. So here we have just some, actual text you can read yourself about, some of the trade-offs we just discussed. And so if we're talking about the runtime of the array list versus the linked list, sometimes we talk about it in this context. So like the time needed to just access a certain element. So we were talking about that in terms of the I want to jump straight into song number 3 in that kind of scenario. So in the array list, that would be constant time because we have an index. So we don't have to loop over everything in the array list to find something and count up okay, I'm going to start at 0 and then I'm going to count until I get to the third one. Nope, I just have an index. I can just jump right in there. And for everyone's awareness, accessing an element at an index in an array is considered a constant time. However, to access, let's say, the 5th item in a linked list, in order to do that, I'm going to have to start at front, and then I'm going to have to maybe make an int, and I'm going to say, okay, the first thing is the first one, count 1, and then follow the arrow to the second thing, count 2, follow the arrow to the third thing, count 3, follow the arrow to the fourth thing, and I'm going to have to do that until my little counter hits 5. And so the relationship between how much code is going to get executed in order for us to find something based on the index is actually based on how many items before it. So in a linked list, that is now linear time to get the nth element out. Now, here we've got another one. Time needed to insert at a certain location. So I want to, in our linked list maybe scenario, I was like, okay, you know what? I found the perfect middle of the playlist song. I want to go in. I want to insert that thing in there. If I was doing that in a linked list, I would have to count from the beginning until I get to that index, right? I gotta count. I'm I want to put it at, let's say, position 5. So I gotta count 1, 2, 3, 4, 5. But then I just make a new node, stick that thing in there, and I'm done, right? That technically, even though I'm not going to continue to the very end of the list, because it is dependent generally on how many items in the list, and for example, we could be doing this with the second to last thing in the list or the very first list, we kind of always assume what we're going to call worst case scenario. I promise you I'm going to talk about that until I'm blue in the face. But in this scenario, we are going to consider that a linear time relationship. In the array implementation, if I want to insert something, remember we had to do all that shifting to make space for it? So I had to touch a bunch of other elements in order to make space for something. That's one of the scenarios with the array list implementation. Or let's say we are in the dreaded situation where the array is full. if the array is full, remember, then what I need to do in order to insert something is I had to make a whole new array that's double the size, and then I had to copy everything over. So actually, we end up with linear runtime for inserting in an array list. So they're equivalent in these situations. Those are the runtime analyses on the array list versus linked list. Does anyone have any questions on the runtime analysis of those two things or how that works? Okay. We are going to evaluate code in a lot more ways than just runtime. So one of the other most common ways in the technical side of things to analyze is not just how quickly is something going to run, but how much extra space it uses. And so like maybe because I'm such a teacher, I think of it in this way, but like I always kind of imagine like, let's say I have a big stack of papers. I'm kind of thinking about, well, how quickly can I get that stack of papers like ordered by name? And do I have like a bunch of space around me to maybe like lay out the papers or make piles or something like that? And I might make a different decision if like I only have my arms to hold the papers versus if I can just like take up this whole floor and make piles or do something like that. It's kind of the same thing in the computer where you not only have to think about how many instructions are going to run, but if you need to say, make another array to hold all of the items as you move them, that takes up more space in the computer's memory. And when we are programming on our laptops, at least in school, my guess is that you have probably not hit a type of code that has been prohibitively memory expensive so that you couldn't run it on your laptop. And that's because actually in like JGrasp and IntelliJ, they have these sort of limits. So they make sure that like if you run bad code, it doesn't just like crash your computer because it accidentally just consumes all your RAM. But very, very quickly in industry, you will get to places where the memory usage is so big that it would never fit on a single machine. And in fact, not only would it never fit on just your dev machine, it wouldn't even fit on a single server box out in our farm under the Pacific Ocean, right? So we have distributed systems, we're splitting these things all over, and so memory considerations are a huge part of industry. Another side of the memory considerations is now we have computers in literally everything, right? Like, my favorite is I'm always like, there's a computer in my watch. Would you even know? No, but it has its own operating system. It has its own memory on my watch, right? You can imagine there's a lot less extra memory space in my watch than there is in my computer. So when you're doing programming for devices, for embedded systems, memory a lot of the time actually becomes the more important consideration than the runtime even. Phones, for example. Now, it is crazy because in the time that I have been teaching computer science, your phone suddenly has almost as much space as your computer does, which is absolutely bananas to me. But phones will always inherently have less space than, say, a laptop. And so a lot of times when you're doing mobile design, memory is also a very large consideration. So a lot of times we analyze memory very similarly to how we would analyze runtime, in that we think of it in terms of N, meaning in terms of how many things are stored in your data structure that you're running your instruction against. So for the array list implementation, the array implementation of a list, remember how I kind of mentioned that you always have a little bit of extra unused space? Because you kind of need to make an array of a set size. And let's say you start with an array of size 10. You slowly fill it up, right? And so at the very moment that you start, maybe you start with one item in your list, you have one used space and 9 unused spaces. And then as that array grows, when we fill it all up, we make that duplicate. Again, we kind of like increase this amount of unused space. So sometimes there's wasted space, sometimes there's not. And so at, sort of its worst, we kind of have like 2n amount of space. Because we sometimes, like at that moment of doubling, we would have like the same amount of empty space as we would have of used space. Versus the linked list, we would maybe call this compact because it always has that linear relationship between the number of elements in your list and the number of nodes that you have. Because you just make a node every single time you have a new item. So the linked list is more optimal in terms of memory usage than the array list. Now, that's the amount of space used overall. We can also think about the amount of space used on a more granular level. And so I think I kind of talked a little bit about how these things work in the computer, but hang on, we're going to go. Somebody asked a really great question about this after class, and I realized we should probably talk about it together. So when I'm talking about memory usage, okay. Sorry. I'm that jerk on the other end that has to make sure that those little privacy things get written, and I always makes me laugh. Oh, okay. There we go. Apparently it updated the last time that I blue screened. Okay, so here we are. So, all right. You're right. I believe you. Okay, so let's think about our memory in the computer. This is a really crappy drawing. Let's call it your RAM. Your RAM in your computer stands for your random access memory. It's the memory that the computer has in order to accomplish all the things you're actively doing with the computer. It's that memory that when you turn the computer off, that also turns off and kind of wipes everything out. In my little teacher paper scenario, you might think of the RAM as like the floor space that I have to like maybe use to organize my papers. When I tell the computer, hey, give me an array of size 3, what it will do is it'll come in here and like, let's say your RAM, like maybe here's like, I don't know, you've got some like stuff in here. Maybe this is your Spotify. I have no idea what you're doing there. Okay, it's arrows. Hilarious. Can you give me colors? Where are my colors at? Okay, you're now oh, there you are. Thank you. Okay, and then like maybe over here, like I've also got like Word open or something like that, you know, and then like I don't know what I'm doing over here. Maybe I've got like a picture or something stored, and you don't know what the RAM in your computer looks like. All of this stuff, that's all controlled by the operating system. The operating system is who decides what goes where. And the operating system, I like to think of them as that, you know, that ultimate dad at the back of the car getting ready for the road trip, you know? And you're like, Dad, okay, we're bringing everything. And your dad's looking at all the stuff on the ground and he's got to tessellate all that stuff into the back of the Tahoe. Okay, if you're not aware, I'm obviously the dad in this situation because my sister can never get it down to a single bag. And you're trying to figure out where to put stuff. Java is my sister who's like dropping off her bags and like, Casey, just figure it out. So when Casey's sister shows up to the memory and is like, okay, I want an array of size 3. What the operating system is going to do, it's going to come in here and it's going to look and it's going to say, okay, let's see. I'm looking for 3 spaces and they have to be right next to each other because they're an array. Sweet, found it. And what's great about that is then if I have something at 0, 1, and 2, when I'm looping over this code, I know exactly where to find things, and it's actually really efficient to get everything right there. But if I have a linked list instead, what happens with the linked list is I make them node by node, right? So maybe like this is where we put the item at 0, and then I come in and I'm like, okay, I need another item for 1, and the computer's like, okay, well, I'll just put it here. It doesn't know they're connected. And 0 kind of like knows where to find 1. And then maybe, you know, like as I'm using my computer, like other stuff gets filled up, you know, things like that gets filled up. And then I come back around and it's time for me to add in like my 3rd element, you know, there's where that was, and that one will point down there. And so you can see that not only do we have this sort of inefficiency because we have to jump all over the memory, but in the array situation, all I had to store was just these 3 boxes for these 3 things. Actually, in the linked list situation, I need a box that stores the value, but I also need a box that stores the arrow. So maybe this is like the value 3, maybe this is like the value 2, I don't know, maybe this is like the value 0. And so actually I end up needing to store per element, not only the value, but I also need to store where the heck the next value is. So if I come back to our discussion here, when we're talking about the amount of space used per element, the array list is minimal because they're all right next to each other. So I just need 1 space in memory per item. For the linked list, there is what we call the sort of tiny extra for each element. And that's why we draw linked lists. like this. This little like divided box is literally supposed to represent like 2 boxes in memory. And we have a box for the element and we have a box for the arrow. So this arrow is the tiny extra of memory usage that we need in the linked list scenario. Questions about any of that memory stuff? Yes, in the back. Ooh, is that related to the number of fields? Is that what you just asked? Yes. So when I have an object, the object has those fields. When I call new whatever that object is, and you know how in the constructor of an object, a lot of times the things you're doing in the constructor is just initializing those fields. Initializing a field, what that literally is going into the memory and being like, okay, here's my size. Put a 0 in here. Okay, here's my like front pointer, put an arrow in there. It is exactly what you asked. It is absolutely partitioning bits of memory. So the more fields you have, the more space you're using. And you probably like remember in 1.4x how, I want to use the word militant, they were about not having global fields. That's because if a field is global, this box gets partitioned in memory at the very start of your object, and it will persist through the entire life of your object. Local variables do this as well, but at the end of a method, the garbage collector literally comes in and is like, oh, I'm done with my method. Clean that up, clean that up. And so those things don't persist as much. So that's why it's very memory inefficient to have a bunch of things in the global fields. Yeah, question. Ooh, good question. So if we have an object, is everything in the fields going to be allocated next to each other? So we will talk about memory in a little bit more detail later in this course, because there are 2 different ways that the operating system kind of thinks about where to put stuff in this delightful grid. It thinks about if the stuff is related, which was what you just talked about, which is called spatial locality, and it talks about how often do you use stuff, and that's called temporal locality. I like to think of this in terms of how messy my bedroom is because I'm terrible at putting my clothes away. You know how you have that back of your closet stuff that you just never really touch? And you kind of live off of the clean clothes that are all stacked in your office chair because you're a bad adult? I think of that pile of clothes in my office chair. It's like literally all the stuff I end up wearing together, and it's the stuff I wear all the time, and so I kind of keep it like easy and at hand. And then that like one nice dress so that my mom isn't disappointed in me that I pull out once a year for Mother's Day, that's like deep in the back. The operating system's doing kind of similar sort of evaluations, and it will do that with your object. It'll think, oh, I'm partitioning all of this stuff at the same time, so it'll keep it together, but it is not smart enough to know that one array is logically connected to another array, but it will probably end up keeping them around and in the same place because you're using your object all at the same time. So it's a temporal situation, but not a spatial situation. Let's see. Yeah, question.
So we discussed how these objects have fields, but they also have like functions and that inside of them.
Yeah.
So for each object that you create, does it have to store like some space saying that, oh, this object has this kind of functionality as well? It doesn't have to create that space.
Yes. Oh my gosh. Okay. If you can't tell, the ECE in me is like, yes, let's talk about this memory so much. Just out of pure interest, how many ECE embedded systems humans are here? Okay, amazing. On it, like everybody, this is just, it's a requirement, it's a graduation requirement, right? That's why we here, and also because this class is so fun. So if you go into ECE or you take a class on assembly, you will learn a lot about what you just asked, because in the computer, there are what we would call spaces in memory that will store what are called function pointers. And there are spaces in memory that have to store the code that you're actually running. So this right here that I've sort of drawn, remember how I was like, maybe this space is Spotify? That space is the code that requires Spotify to run. Obviously, it would be more than 2 boxes. And within those boxes, there's like parts that are like, here's the actual like characters of the code that needs to get operated. And then there will also be spaces in memory that's like, okay, well, like maybe this is a function stored in memory, and then this is an arrow that takes you to the function that gets called from within that function. So we need memory to store the code itself, and we need memory to store how to get from that code to other bits of code. Again, the operating system is managing all that. A language called assembly, we'll figure it out. It's called stack frames. You can learn a ton more about it if you take 374 with me too. Good times. Yeah. Any other questions? Yeah.
Is this still a problem to like today's computers? It's like everyone has more than 8 gigabytes.
Okay, so the question is like, is this a problem? Like, is this a limiting problem in your computer? Okay. Once upon a time, there was a magical decade of opportunity and innovation. And we all had these magical boxes on our desktops that they told us you can go in and like go to places all over the world and download photographs. And the photograph would start at the top of your screen in 1995, and hopefully by the end of the Sailor Moon episode I was watching on UPN 11, we would get to the bottom of Sailor Jupiter's shoes. You know what I mean? Like, it's that kind of situation. Obviously, we live in slightly different realities now than we did then. However, we ask so much more of our computers. And so I don't know how many of you like look at the real specs on your computers when you're buying them these days. But when you're looking, sometimes you might look at that RAM. RAM traditionally is around 8 gigs, but you can get RAM that's much larger. The larger your RAM is, the more your computer can do at once.
Is that the computing ability?
Sorry, say it again.
I mean, it's the RAM means the computing ability
Like, does the RAM mean the computing ability of the computer? Is that what you're asking? Yeah. So RAM technically stands for random access memory, and it just means like how big this grid thing is. The actual ability, so like this grid here, I wish I had a better cultural touch point for this, but has anybody ever seen the movie Spirited Away? Okay. Okay, you know down in the boiler room, man, what is his name? Why can't I remember his name off the top? Somebody has it. Yes, big Spider-Man. Yeah. He's got a really charming name, and he's really nice to Sin. But it's this operator of the boilers. He's got all of these arms, and he's doing a ton of things at once, right? Like, he's got an arm where he's like drinking tea, and he's got an arm where he's fueling the boilers, and he's got an arm where he's like taking instructions. I think of those arms as the CPU. The CPU is the thing that's actually executing instructions. The RAM is how many boilers he has, how many things he can actually do at once. So it's a combination of your RAM and your CPU that accomplish how many things your computer can do at once. So you can think of the CPU as how many arms. Sometimes you have something called a dual processor. That literally means it's like you kind of have 2 computers in one doing instructions at once. But it's all, of course, limited by how much space you have to actually like place these puzzle pieces together as well. Yeah. Yes, somebody said it. What is his name? Yes, Babaji. What is it? Kamaji. You're so right. It's Kamaji. Yes, thank you. Also, if you haven't seen that movie, it is absolutely one of the best movies ever. You should go watch it. Yes.
Is that why they have like different graphic settings on games? Like if you want to hit like high, medium, or low, like is that like dependent on like if you want to do high, that's gonna let you use more RAM?
Yes, absolutely. So, for example, in computers, in games, that is some of the largest memory requests of your RAM in existence. And so when you change the graphics levels, it's essentially changing how many of these boxes you're going to partition. So that's why, sir, for example, 16-bit games, you can imagine, use a lot less memory because it's like those pixels are physically bigger. The more detailed your picture gets, the more pixels, the more of these spaces you got to take out. Okay, here's what I'm going to say. I thank you all for asking these questions. I wanted to take this time because when we're talking about runtime and memory, I wanted you to understand what's really happening under the hood of the computer. I am not going to get time in lecture to go through the details of the other items in here, but I have structured these slides so you can read them, but I want you to know a little bit about what you need to pay attention to here, okay? So if you scroll through, you will see that I have added in here how the stack ADT is impacted by array or linked list implementations, how the queue ADT is implemented in array versus linked list. And then on Monday, we're going to come back together. I'm going to give you a brief review of that, and we're going to talk about the map ADT in the same concept. Really quick, I know I promised you the solutions to what we were talking about during the warm-up. Here is my justifications for the warm-up for either the linked list implementation or the array list implementation. I will tell you, personally, the top ones are the ones that I would have assumed. But like I said, there's no wrong answers. Oh, it just disappeared. For no reason. I literally don't know why. Okay, well, it'll be posted on the website, so you should go look at it. And on Monday, come prepared to do more debates about implementations between lists, stacks, and queues. Have a great weekend, everyone. I'll see you Monday.